Hey all, I'm Despi and welcome to another course of our digital forensics class. And today we're going to talk about network forensics. So briefly we'll talk about how to acquire data using various ways, and then we'll just point you to some videos about certain tools. The most easy of all being Wireshark, that you will be able to visualize network packets. So you might have heard about the OSI layer, which kind of separates the network, all the network frameworks that you will be using into different layers. Okay, so as I'm pointing out here, the first layer is defined as a physical layer. So you can imagine that that being, for example, the cable that the data is flowing through, or it might be some fiber optic cable, right? Or it might be some UTP, some twisted pair cable, or it might be some coaxial cable. There are many different physical layers. Then on top of those, we might have the data link layer, which sometimes it can be Ethernet, or it could be other more obsolete these days protocols. But anyway, I just want to point out here that all these are not cast in stone, and this idea of separating things in these layers can be useful sometimes, but it also can be very harmful, because a lot of in a lot of real world cases, things can flow between layers. So you might have something that controls something else in a completely different layer. So you shouldn't really be using this framework in a way that hinders your understanding. It's just something there to help us navigate the complexity of very, very low level stuff, like how the signal propagates through the medium, to pretty high level stuff, like how is the cookie affecting my HTTP2 session. Okay, so when you're acquiring data, you can imagine that you might acquire in kind of all these different layers. Like you might physically tap on a link, or you might send the packets. You might be listening on an HTTP proxy server, and you might be getting the HTTP packets there. So in both cases you're acquiring data, but in one case you're getting like the actual signal with all the envelopes up to a point, and in the other case you're pretending you're an HTTP proxy and you're just copying a certain protocol. That's why we need to have some distinctions here, how every layer works. So when we want to acquire data in the physical layer, as we say here, we have different conduits, right? A coaxial cable, you might have seen them, I guess these days mostly in TV antennas, is where you would normally see a coaxial cable, or if you're a ham radio enthusiast, so you might also see a coaxial cable there. And this is a center conductor that around it has a shield, okay, another metal layer that forms a shield and shields it from interference. So this also shields out things outside of the cable from interference caused by the current passing through the cable, right? So it kind of forms a Faraday cage, as we say here. Now this is a single channel passing through there. So if you can kind of tap in without connecting, the outside of the cage to the internal cable, then you can get these signals. If you look at an Ethernet cable or a phone cable, you might see that it has from 2 to 4 to 8 different little cables in there. And these cables, if you open the Ethernet cable, you will see that they are in pairs of twisted cables, right? So there would be 4 pairs of twisted, 4 sets of twisted pairs. And for that reason, it's called UTP, twisted pair cable. And it's unshielded because if we can twist the cables between them, and then they somehow negate each other, the interference they might cause. So we don't really need the external shielding. That's why it is unshielded, and that's why it's called UTP. Now, these Ethernet cables, normally they would connect to, for example, a switch or a tap, as we're showing here on the inside. And we say tap because taps usually allow you to tap in some sort of communication. So I might actually have, one, as you see here on the right, it says network and monitor, if you can make it out. So you might have like some network coming in and some network coming out from here, and then you can also monitor the same traffic by putting more cables in this. And this can be a completely passive tap. So that means this device in here, just whatever signal it gets on these twisted pairs that are landing in here or sent out from here, it just copies them on the monitor port. And if this device, and this XCI device, is actually very good, then it should do that in a way that when you're when you're seeing the physical properties of the signal propagation there, it shouldn't really show any difference. So people shouldn't really understand that you're monitoring from these ports when data passes from these ports. And certainly this company XCI does its job pretty well. So what about when we have like fiber optic cables? How do you do that? Well, you have a light pulse passing through a cable. So if you want to physically tap that, you need to intercept that pulse and then produce another pulse there. Just hinting at how this might work, right? And you need to do that pretty quickly in order for you to maintain the characteristics of that L1 collection. Now, I'm very happy that I have found this picture for you guys, and you can enjoy it. This is called a vampire tap. Okay, you can imagine why it's called, because in here there are like little metal like needles that can actually tap into the cable like vampire teeth and can intercept the data, and it can give back to you the data over this RS-232 port, serial port here. Now, this is a pretty dated mechanism, but still very interesting, because these days would have no one would tap like a link so slow that it can be passed. It can be intercepted through a serial port. That would be pretty slow, but the idea these days still remains the same. Now you can imagine that if you do that, and we're still talking about acquiring data in L1 in the physical layer, then you're changing the propagation characteristics of the signal in here, right? So you might increase the resistance of the cable. That might show up in upper layers, because now the link might have more errors, right? So imagine you're a system administrator at the network that you're having sensitive data passing through. If you have access to certain links, you might want to be monitoring that, because if suddenly you see that, oh, now my propagation characteristics of the signal, I'm having a lot of errors in the lowest layers, 99%, most probably there is just a switch going bad, or there is a cable going bad, but there is 1% there that some adversary might be tapping physically on your links, and it's good to investigate. So you always need to build some sort of visibility into your networks. Now, could you do that without actually tapping in here? Think about it. Think about the induction coils, and if this is a shielded or unshielded cable, how close you have to get. How about maybe could you just untwist the cables, right? That's another idea. But there could be ways. Now, there have been, it's public knowledge these days, that big nations and big actors, let's say, have the capability. They have submarines where they can actually tap undersea cables, or do certain operations on undersea cables. That the internet is, at this point, continents are interconnected mostly via undersea cables, or Starlink, types of devices that maybe they're more prominent in the future. But right now, we might have an underwater cable, running through the Atlantic. Actually, multiple of them, connecting continents between them and countries between them. So if someone can tap in that data, it's going to be they're going to have access to an insane amount of information. So we know that there are submarines that can do that. They can go, they can attach themselves on a cable, and then they can drain the water and have a certain space there, with air, so that engineers can work and tap on the cable. But even if you just cut a cable, right? If you cut a cable, the internet routing protocol, which is the current selected routing protocol for the internet, which is BGP, the Border Gateway Protocol, is going to, if it detects an error like that some link is cut, it's going to reroute traffic through other links. Well, those other links might be preferable to you because you might have installed some taps there. So that's another way that you can actually tap a link that you don't have access to, by tapping where it's going to go and then destroying the original link. Okay. Now, what about when we don't have like a cable, but we have like wireless data? What happens in that case? Well, it's even better. Wireless data, they're made to be tapped, right? They're made to be listened to. So when you have wireless data, for example, if you have an access point, everyone knows the SSID of that access point. Okay, maybe that's cool, right? Everyone should know the SSID, and you can also hide it if you want. But what about the MAC address? And I hope you guys remember what a MAC address is here. We have talked about it's a media access control. It is like a specific identifier of every network card in existence, right? So every network card, your Wi-Fi card on your cell phone, has a certain MAC address, and your Wi-Fi card on your laptop has another MAC address, and my Wi-Fi card on my laptop has another MAC address. And some bytes of that address can reveal who is the maker, for example, or other model numbers and certain stuff like that. So what about MAC addresses? Is that fair game? Like, you're listening to some Wi-Fi communication. Should you be able to see the MAC addresses participating in that, in that chat? Well, if you think you shouldn't, then maybe you shouldn't be using Wi-Fi, because you can actually see the MAC addresses of the participating wireless cards. You might say that, okay, that's fine, right? I'm going to encrypt everything on top of that. But the exploit might also tell you what are the supported encryption algorithms that you have, and which actually MAC addresses, which of the MAC addresses are actually associated. And sometimes you might get like just plain data, like you're just there might be no encryption. Like let's say you go to a public access point, right? And there is no password there. Well, then you can just get all the data that's passing through. And if someone, if you go into a public Wi-Fi access point with no password, and now you're logging in to a web page that's also not on HTTPS, well, then everyone can just probably see your unencrypted password flying, on the ether, right? How can you get that data? So you need a card that can enter monitor mode, and monitor mode is a kind of a mode where you can set the card, I want to just listen in and I won't transmit anything. Certain firmwares on cards have this turned off, but you can get cards that allow you to set them to enter in monitor mode. Usually a card made, having an Atheros chipset, again, that's an Atheros chipset, you might want to look, you want to buy certain cards like that. On Unix systems, they will allow you to enter monitor mode, but there are other makers that also allow you to do that. Then, if you're on Unix, there is this suite of programs called AirCrack NG for the next generation. There used to be another AirCrack, and you can use certain programs, from that suite to acquire wireless data. Now, what about WPA and WPA2 even passwords, right? Let's say you're in a Wi-Fi that has WPA, or web, even worse, which is a weaker encryption mechanism. So let's say you're there and you want to understand what's going, sniff the Wi-Fi, but it's encrypted. So everything you're getting is okay. You're getting maybe the MAC addresses, but then it's an encrypted frame. Well, you need to crack the password. If you join that Wi-Fi, like if you had the password for that Wi-Fi, then you would be able to decrypt the data on that Wi-Fi. But right now you don't. So how do you do it? Well, when a client joins a Wi-Fi password, it kind of has the password, right? Let's say I'm allowing you to join my Wi-Fi, and my password is, for example, I don't know, password 123. So you can hash that password through a hash that you have agreed, and you present that hash, and I'm telling you, yeah, that hash is fine, you're allowed to join. So we set up another password for that session, and we can start chatting. So if you're someone else, if you intercept that hash, then you can start trying to crack that hash, right? You know the hashed password, and you will have a very big machine, right, that can do many hash checks per second, and it's going to do a dictionary attack on that password. And if indeed my password 123, then pretty quickly you would find that, password 123 hashes to the same hash that I saw over there, and that's password for that Wi-Fi. But the question is, like, how can you have them send the password, because they might be authenticated already, and they don't care, they have established another session key and whatever. Well, on most Wi-Fi protocols, there's this feature. It's not a bug, it's a feature, right? But you can actually de-authenticate them. So you can send some frames, pretend you're the access point, because you know the access point MAC address, and you can send some frames from that MAC address, forged, of course, because you're not the access point, and then saying, de-authenticate. So they de-authenticate, and then they re-establish their connection, and then you have that hash, and you have the Wi-Fi. You have something to crack to find the Wi-Fi password. Okay, just kind of a walkthrough on how this process works if you do it. Now, what about higher layers? Okay, in the older times you had this idea of a hub and a switch. So a hub is something that whatever it took on one port, let's say it had like 10 Ethernet ports, and whatever it heard on one port, it would repeat it on the other 9. So in this case, you can imagine that if you were able to tap on a hub, that's pretty great because you could get the traffic for everyone else, right? And yeah, I mean, like it's pretty easy to explain. But switches, they have this thing called a CAM table, and a CAM table associates the port with a MAC address. And I hope you see why it's called a CAM table, because it's the reverse of the MAC here. Okay, it's a funky naming scheme, right? So the switch knows at which port it has, which MAC address, and when it gets something from one MAC address to another MAC address, it will only send it on the right port. That is, first of all, the correct thing to do, instead of the hub that just, broadcasts everything. But apart from that, it's more economic, right? It can do that quickly, switching, by an efficient algorithm, and therefore it can save power and cycles to write other data to other ports that they need it. So usually switches would have a better performance, like switching performance, of course, right, than a hub. Now, how do you tap on a switch? Okay. Sometimes switches, because they have like now state internally, you might need to administer stuff. They might have like some sort of admin interface, especially industrial level switches, they do have some sort of interface. If you can access that interface, then maybe you can just set a port to be a span port, which is just a mirror port, right? That's pretty awesome. So you can just get the data from one port or all ports, maybe copied to the span port. In the case that you copy all ports to one span port, and all the other ports are going like full speed there, let's say it's a 1 gigabit switch and it has like 10 ports, and all 9 other ports are like going full throttle 1 gigabit, then you might have some hard time copying that data quickly over to the span port. Okay. But what if you don't have like access there? Is there any trick you can do? Yes, you can. So there's an interesting little hack that if you start creating random MAC addresses and you're pretending you're a different person every time trying to talk to that switch, then this table they have, it's going to fill up by MAC address listening to. And this is, of course, what I'm saying here might not apply to you. I hope it doesn't apply to your workplace switch or your university switch, because hopefully there have been protections there. You can even be very strict on a switch. You might have like an authentication on which MAC address to, which MAC address goes to which port. So that's a pretty solid setup there. So the attacker will need to know which MAC address to use for each port. But anyway, let's say that you find a switch that's open to some abuse, as we're describing here. Then you can pretend you have many different MAC addresses, fill out the table, and when that table fills up and can register any other associations, it just goes back to becoming a hub in a sense, right? Or let's say you want to tap traffic that goes to a specific IP, or a specific MAC address here, and therefore a specific IP. you might start advertising that you have that MAC address, right? Let's say you're going to tap traffic that goes to IP 1.2.3.4, and then that MAC address is, for example, AA, BB, CC, DD, for example. You're going to start pushing out packets that I am AA, BB, CC, DD, having that IP, right? Therefore, sorry, I just got this wrong. I'm saying I should say that you will start advertising packets that that say that IP 1.2.3.4 is on your MAC address, not the AA, BB, CC, DD that was the original MAC address. That the 1.2.3.4 IP has your MAC address, which might be like E, FF, EFF, for example, right? So by doing that, you are kind of interfering on the address resolution protocol, which is what connects IPs to MAC addresses, and you're spoofing on that on that level of that protocol. Therefore, confusing another table here, not the CAM table, but the ARP table that this switch has, and injecting your own association of IP to a MAC address, and therefore again getting the data back. Now, whatever of these two things you do, you can imagine that the switch is going to complain a lot, right? Because things are happening on its critical table. So this is definitely not a technique that you should be using if you want to not be detected. You're definitely going to be, causing a lot of noise on the network if you start doing stuff like that. Therefore, you shouldn't be doing it. And sorry for the mistake I made on the ARP spoofing example. Now, further on, how do you acquire data? On Unix, there's this library called libpickup, and this is the library that most of the programs that we will be using uses, under the hood. It's called libpickup because pickup stands for packet capture, and you can imagine that it has this envelope format, the pickup format, that in there it can contain many network traces. Now, what about BPF that I'm mentioning here? BPF stands for Berkeley Packet Filter, and it was a language that was designed originally to be able to filter packets, right, in BSC systems. And it's a pseudo language that contains things like, which hosts are involved or which ports are involved. And then you can also chain things together, via logical means, okay? So by using BPF expressions, you can filter on data. Again, let's see some more BPF types. I said host here, or net. You might just talk about whole subnets here. You might say, 1.2/16. That means all the addresses that start with 1.2, right? So 1.2.3.4 and 1.2.4.5 both would belong under 1.2/16. If you're a bit, rusty on your CIDR, network addressing stuff, please take some time to review that info from the internet. Now, you might also have like port ranges here, from an application connect from a source port to a destination port, and all that good stuff. Also, you might be able to specify different protocols like Ethernet, or wireless, or IP, or IPv6, and all the protocols we kind of talked about. And you might also be able to specify like flags, right, in these protocols. So here we have just a very trivial example. Okay, if we want to keep traffic that involves this IP and all other IPs except 10.1.1.1, okay, and on these 3 ports. Okay, let's see how we do it. On these 3 ports, you see we can group these 3 ports here, okay, port, or port, blah blah, or port, blah blah, and we can use the parentheses here to group them together, and then prefix them with an and, okay, so we kind of solve that part, and then we can use another and here to connect these things together, and not host 10.1.1.1. Okay, so we also did that. And in the beginning, we also said that we care about traffic that involves this host, so we start by this host, blah blah, and not host the other one, and this set of ports. Okay, it's pretty, it's pretty self-explanatory. Now, the tool that I would like you to focus more than Wireshark even would be TCP-dump, because it allows you to examine data from the console, and allows you to also capture data easily from the console. And so here, for example, in this command line, we see, okay, TCP-dump, just focus on the I parameter here, and we say, okay, I means interface, so we're capturing from this interface, and we're passing it a string that says not TCP, not TCP and port 80. So let's think about it. It's going to capture all the other traffic that's not at the same time TCP and port 80. So TCP, port 80 is usually HTTP, and TCP is a TCP protocol. So what do we see here? We start seeing, for example, some things that are UDP. Well, that checks out because we said not TCP, right? But also and port 80, right? So this kind of checks out because it's a completely different protocol. So another thing here is, like, if you try to capture data over a link that is very, very fast, it might be impossible for the system to do that, because it might not have the memory bandwidth or the bandwidth in the PCI bus or the CPU to actually capture all these packets if you're trying to tap an ultra fast link and get all the data out. So in that case, TCP-dump would just drop packets silently. It would say, I lost a lot of packets, and sometimes you might even not know how many packets dropped, because it might be impossible for it to detect how many packets dropped. But on a consumer level link, you should be good to go. Now, what if we have like files passing over the network? Could we carve them out like we did with DD? Well, yes, there are ways. And if you're still using, like, for example, TCP-dump or some console program, you can use this tool, TCP-extract. Look, it's very similar to Foremost, like that we talked about before, right? It says you can see it's very easy, right? It has the number of bytes, the prologue, and the epilogue of that file type. So it just looks on the packets if it can decode them, looks for these prologues and epilogues, and if it's below that number of bytes, it's going to extract it and say to you that, oh, I found, for example, let's say a PEG file. For Wireshark, there are some amazing videos on YouTube, and we just point you to these videos for now, because the people who have recorded them have done a very good job. Wireshark is like TCP-dump that we showed, but it has a GUI, so you can actually do way more interesting stuff directly. So it has ways to detect, for example, a conversation. So it can follow different packets that should belong in the same conversation. Or it has ways to decode, also TCP-dump has that, for example, not passwords, but protocols that might have very simple ways to transmit passwords, right? And you might even see the actual password because it can decode the protocol, a very simple protocol, and it can show you the actual password that might have been used for a certain communication. Or it might show you other interesting properties of that connection. So yes, please check these links that we're mentioning here. And for Wireshark, this is a pretty solid series that will get you definitely up to speed to solve any dodgy problems that might give you involving Wireshark. So that's it. It's a very simple module, and it's just data carving out of a file now, and that file is our packet capture. So you guys should be set up. Of course, network forensics might involve way harder setups, right? Very bizarre protocols, or we might be unable to actually capture all the data, so we might need to infer a lot of stuff from sample data. But we hope that this is a good start for you to start seeing how doing network forensics looks like. Thanks for attending this lecture too, and we'll see you guys online.